Let us look at convergence divergence theorems of series. So monotone convergence theorem for series of non-negative terms. Let's look at this theorem. Given a series of non-negative terms, that is summation I equal to 1 to infinity of u sub I with u sub I greater than or equal to 0 has a sequence of partial sums. So the sequence of partial sums for n terms is defined by S sub n is equal to summation I equal to 1 to n of u sub I. Now, since u sub I is greater than or equal to 0, the sequence of partial sums is monotonically increasing. So which means exactly one of the following holds. If the sequence of partial sums is bounded above, then the sequence of partial sums is convergent. And hence, the series is convergent. And if the sequence of partial sums is unbounded above, then the sequence of partial sums goes to plus infinity. And hence, the series diverges to plus infinity. Okay, let's look at an example for this. So we have the summation from n equal to 1 to infinity of 1 by 2 to the power of n, an infinite series. Now, for all n in natural numbers, 1 by 2 to the power of n is greater than or equal to 0. That means all the terms are non-negative. Now, let s sub n equal to summation I is equal to 1 to n of 1 by 2 to the power of I. That is, s sub n is the partial sum up to n terms. Just for understanding, I have expanded it. So we have the sequence of partial sums is equal to, first term will be 1 by 2. The second term of this partial sum sequence will be 1 by 2 plus 1 by 2 square, 1 by 2 plus 1 by 2 square plus 1 by 2 cube, and so on. And this is the nth term of the partial sum sequence. Since each term added is positive, the sequence of partial sums is monotonically increasing. Now, the nth term of the sequence of partial sums is a geometric series with first term 1 by 2 and a common ratio 1 by 2. And we know the formula for S sub n, finite sum of a geometric series. So S sub n is equal to A, that is the first term, times 1 minus r to the power of n. So 1 by 2 to the power of n divided by 1 minus r, that is 1 minus 1 by 2. Now 1 minus 1 by 2 is 1 by 2, 1 by 2, 1 by 2 cancels out, and we are left with 1 minus 1 by 2 to the power of n. Here 1 by 2 to the power of n. So when n is 1, it is 1 by 2, 2, 1 by 4, 3, 1 by 8, and so on. So that means it is a number which is less than 1. And 1 minus a number less than 1 will be less than 1. So for all n, S sub n is between 0 and 1. Hence, the sequence of partial sums is bounded above by 1. So the sequence of partial sums is monotonically increasing, as we have shown here, and is bounded above, as we have shown here. Hence, the sequence of partial sums is convergent. Therefore, the series itself converges. Now let us look at nth term test for divergence. If a sequence of partial sums is convergent, then its general term u sub n tends to 0. So we have the sequence of partial sums. S sub n is equal to S sub 1, S sub 2, S sub 3, and so on, where S sub n, a particular term in the sequence, is equal to the summation I is equal to 1 to n of u sub I. So there exists L is equal to limit as n goes to infinity of S sub n, since the sequence of partial sums is convergent, which also means that limit as n goes to infinity of S sub n minus 1 is equal to L. Since shifting the index does not change the limit. U sub n is equal to S sub n minus S sub n minus 1 for all n greater than or equal to 2. Why this particular condition? Because if we say 1, then we will end up with S sub 1 minus S sub 0. S sub 0 is not there here. So that is why n greater than or equal to 2. Limit as n goes to infinity of u sub n is equal to limit as n goes to infinity of S sub n minus S sub n minus 1. So we are taking the limit of both the sides as n goes to infinity. And this is true mainly because the limits are linear. Again, using algebra of limits, we can split this into two limits. Limit as n goes to infinity of S sub n minus limit as n goes to infinity of S sub n minus 1. They both are L. So L minus L, which is equal to 0. So we have shown that if a sequence of partial sums is convergent, then its general term u sub n tends to 0. Again, let's look at an example. And this time we have summation as n goes from 1 to infinity of 1 by n. So for all n in natural numbers, 1 by n is greater than or equal to 0. All are non-negative terms. So hence the terms are non-negative. Let S sub n is equal to summation I is equal to 1 to n of 1 by I. So the sequence of partial sums would be S sub n is equal to 1, 1 plus 1 by 2, 1 plus 1 by 2 plus 1 by 3, and so on. And this is the nth term of the sequence of partial sums. So S sub n is equal to 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 and so on up to 1 by n. So I have taken the nth term and I have included many more terms in the series. Here I am grouping it in a particular manner to do some estimation. So here first term remains as it is, second term remains as it is. Now 1 by 3 plus 1 by 4 I group it together. So there are two terms here. Then I take the next 4 terms and group them together. Then I take 8 terms, then 16 terms, and so on. So each group from the third doubles in size. So let's look at the third group. 1 by 3 plus 1 by 4 is going to be greater than or equal to 1 by 4 plus 1 by 4. So how did I get this? What I have done is I have taken the lowest number. Here 1 by 4 is smaller than 1 by 3. So if I take 1 by 3 plus 1 by 4, it is naturally going to be greater than 1 by 4 plus 1 by 4. And combining 1 by 4 2 times gives us 1 by 2. Now let's look at the fourth group. 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8 is going to be greater than or equal to smallest number in this taken that many number of times. So here there are 4 terms in this. So we take 4 times 1 by 8. So 1 by 8 plus 1 by 8 plus 1 by 8 plus 1 by 8 gives us 4 by 8, which is equal to 1 by 2. Fifth group. So again 1 by 9 plus dot 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 plus 1 by 16 is greater than or equal to 8 times the smallest number, that is 1 by 16, which again gives us 1 by 2. So what that means is every group from the third onward adds at least 1 by 2. So after k such groups, the last term added is 1 by 2 to the power of k. So the corresponding partial sum is S sub 2 to the power of k. Just try to figure out what is happening here. Now, S sub 2 to the power of k is greater than or equal to 1 plus 1 by 2 plus k minus 2 times 1 by 2. Because why minus 2? Because the first two terms, 1 plus 1 by 2, we are taking as it is. And then we are looking at it from third group onwards. So that is why k minus 2. Simplifying that, we get S sub 2 to the power of k is greater than or equal to 1 plus 1 by 2 plus k by 2 minus 1. Minus 1 plus 1 cancels out and we are left with S sub 2 to the power of k is greater than or equal to 1 by 2 plus k by 2. Now let k go to infinity. What happens? 1 by 2 plus k by 2 goes to infinity. So which means partial sums grow beyond all bounds because S sub 2 to the power of k is going to be greater than or equal to this, and this goes to infinity. That means this also goes to infinity. So that's how we can say partial sums grow beyond all bounds. So to conclude, S sub n is increasing, terms are positive. S sub n is unbounded above, which implies S sub n goes to plus infinity, and which means that the series 1 by n diverges. To summarize, we have seen the case of S sub n is equal to the summation I equal to 1 to n of 1 by 2 to the power of I. And S sub n is equal to summation I is equal to 1 to n of 1 by I. Now the terms 1 by 2 to the power of n shrink very fast. So the partial sums stay bounded. The terms 1 by n shrink too slowly. So the partial sums grows without bound. But remember, both satisfy limit as n goes to infinity of u sub n is equal to 0. But only one has bounded partial sums. So in short, for series of non-negative terms, convergence requires u sub n going to 0, and bounded partial sums guarantee convergence. That was convergence divergence theorems of series. Now, if you found this session helpful, please do like, share, and subscribe. Comments, suggestions are always welcome. Thanks for watching. See you in the next session. That's it for now.